Hey guys, my name is James Jones, and this is my Lab 2 motion of a falling object. So, in this lab, we aim to investigate the motion of an object as it falls from rest due to the force of gravity. And we're going to compare the motion of that object with two computational models that we make based on Newton's second law. One of them is going to account for air resistance, and one of them won't. And for this lab, I chose to track the motion of a paper ball after I dropped it from shoulder height. So, first off, what is the momentum principle? In this lab, we used a form of Newton's second law known as the momentum principle. It can be written as the final velocity equals the initial velocity plus the net force divided by mass times the change in time. So, because the final velocity does not equal the initial velocity in this case, we know that there must be some acceleration and the net force cannot be equal to zero because acceleration equals net force divided by mass. So, what's causing that acceleration to happen? In this lab, it happens to be the force of gravity, which causes the ball to accelerate as it falls through the air. So we're going to explore two models where the net force is simply the weight force exerted by the Earth, and another where the net force is the weight force plus the effects of air resistance. So, for tracking the motion, I used a program called Tracker to analyze the motion of the paper ball as it fell from my hand. So I tracked the motion of the ball in each frame, and I applied this data on a graph, as you can see over here. So, for my computational models, we used a program called GlowScript. And the first thing that I had to do was put in my initial conditions, which included the mass of the ball, the initial position, and the initial velocity, which was 0 because it started from rest. And then I had to put in the force of gravity on Earth, which is negative 9.8 meters per second, is the acceleration caused by gravity. And that was all I had to do for the first model. And then the model that incorporates drag, I also had to add a proportionality constant. So as we can see over here, here is how we incorporate the momentum principle into our model. So in the first model here is the one without drag, where we have the net force is only the weight force, which we put as the ball's mass times the force of gravity times the unit vector in the direction of gravity, and all that to the negative power because it's going down. And then we define the ball's velocity just to be Newton's second law, where the ball velocity equals the net force divided by mass times change in time. And we also updated the position to this formula as we did in the last lab. So as you can see here are our results. We have the experimental data in blue, the model data not accounting for drag in red, and the model data with the gravity plus drag in yellow. So as you can see, we had a great discrepancy in the actual data versus the model data that did not account for air resistance. And this is because with the model data that does not account for air resistance, the velocity simply keeps increasing faster and faster due to the acceleration from gravity with nothing slowing that down. But in reality, the experimental data was much closer to the model data with drag because we have the drag that slows down the acceleration and makes less of a slope in the actual line, as you can see here. So the model data that was compared to the experimental data with drag is much closer together, and then the discrepancies that we see here could be attributed to human error, such as just the motion in tracker, shakiness of the camera, and just things like that. So, moving on. I just said what our results meant, but do any of our models predict a terminal velocity? Well, to answer that question, we have to say what a terminal velocity is. And that's when the drag force on the object is equal to the force of gravity on the object, and the net force becomes 0 and the velocity becomes constant. So we can see in our model, accounting for drag, that our velocity starts to slow down, but doesn't quite reach a terminal velocity. We can still use this model to predict the terminal velocity, but we would need it to run longer. As you can see over here, the velocity starts to slow down, but it doesn't quite reach that terminal velocity. So that begs the question, what if the object was thrown downwards? If the object was thrown downwards, the terminal velocity that it would eventually reach would be the same as the terminal velocity that this object would eventually reach starting from rest. However, it would reach this velocity much quicker. And we know this because the object would still have the same acceleration from gravity, but it would just have a faster initial velocity, meaning that it would get to this point faster and eventually reach the terminal velocity. So, that should be all for my lab today. I thank you for your time and have a good day.